This tiny point of light contains more space than the human mind can imagine. Right now, something is happening to the universe that you cannot feel, cannot see, and were never meant to notice, because space itself is stretching in every direction at once, carrying galaxies away from one another across distances so vast that even light requires billions of years to cross them. And this expansion is not slowing down, but accelerating, driven by forces we still do not fully understand. Every star in the sky, every galaxy ever observed, and every atom that makes up your body is caught inside this process, all of it tracing back to a single moment when space, time, and energy first appeared. So to understand what the universe is doing now and what will ultimately happen to everything that exists, we must begin at the very beginning. When we look up at the night sky, it appears calm, stable, and eternal, like a vast and silent backdrop that seems unchanged across generations, creating the impression that the universe has always existed in this form and will continue indefinitely beyond human time. While stars appear fixed in familiar patterns, galaxies seem distant and unmoving, and the immense scale of space makes it difficult to imagine that anything so large could be dynamic or evolving in a meaningful way, even though, in reality, the universe is not static at all, but a system in continuous motion, shaped by expansion, gravity, energy, and time acting together across scales far beyond everyday experience. Light traveling through space does not arrive instantly, but moves at a finite speed, taking years, thousands of years, or in many cases billions and billions of years to reach us, which means that every distant object we observe is seen not as it exists now, but as it existed deep in the past, turning the night sky into a layered archive of cosmic history recorded in traveling light. Nearby stars reveal relatively recent chapters in that history, while distant galaxies show us a universe that was younger, denser, and more extreme than the one we inhabit today. And by carefully comparing these layers, astronomers discovered that the universe has not always looked the way it does now, but has evolved steadily over billions of years from a much simpler initial state. Only within the last century did clear evidence appear showing that space itself is expanding and that galaxies are moving away from one another, not because they are flying through space, but because the space between them is growing, revealing that the universe has a history, that it began in a radically different condition, and that its present structure is the result of physical processes unfolding continuously since that beginning. This discovery also revealed something deeply unsettling, namely that the universe does not revolve around us, that our planet occupies no special position, and our galaxy is only one among hundreds of billions scattered across an immense and evolving cosmos, governed by physical laws that operate without intention or purpose, shaping stars, galaxies, and black holes with no regard for human meaning or desire. And yet, within this vast and indifferent system, something extraordinary has occurred, because in at least one small region of space, matter became organized enough to observe itself and to ask questions about the reality it inhabits. As atoms formed molecules, molecules formed complex structures, and over immense spans of time, those structures gave rise to life capable of memory, adaptation, and awareness. From that awareness emerged curiosity, measurement, and the ability to construct explanations, allowing a small part of the universe to reflect on its own existence. So every observation we make and every theory we propose is the result of a long chain of events linking the deepest laws of physics to conscious experience. We are not separate from the universe we seek to understand, because our bodies are composed of the same elements forged in ancient stars, and our thoughts arise from physical processes
governed by the same laws that shape cosmic structure, meaning that when we study the cosmos, the universe is, in a very real sense, examining itself through the minds that emerged within it. To understand where the universe came from, how it evolved into its present form, and where it may ultimately be going, we must follow the story back to its origin, to the moment when time itself first appeared and the history of everything quietly began.
At the beginning of the universe, there were no stars, no galaxies, and no planets, because even the most basic structures required to build them did not yet exist, and everything we now experience as space and time was compressed into an extreme physical state beyond direct observation. This moment is often called the Big Bang, but it was not an explosion into empty space because there was no surrounding space at all, and instead, space itself began to expand everywhere at once, carrying energy and matter along with it. There was no center to this expansion and no edge moving outward because every region of space began expanding away from every other region simultaneously, meaning that from any point in the universe, the expansion would appear the same. In these earliest moments, the universe was unimaginably hot and dense, filled with energy so intense that stable particles could not yet exist for long, forming and vanishing in a rapidly changing sea of motion governed by unfamiliar physical conditions. As space expanded, the universe cooled, and as it cooled, energy changed form, allowing the first elementary particles to appear, including quarks and electrons, which collided, separated, and recombined at extraordinary speed. Within fractions of a second, quarks bound together to form protons and neutrons, creating the basic building blocks of atomic nuclei and setting the stage for the existence of matter. Minutes later, as temperatures continued to fall, these protons and neutrons combined to form the nuclei of the simplest elements, primarily hydrogen and helium, elements that would later fuel the formation of stars and galaxies. At this stage, the universe remained opaque because free electrons scattered light constantly, preventing radiation from traveling freely through space and keeping the early cosmos hidden from view. Hundreds of thousands of years later, conditions finally allowed electrons to join atomic nuclei, forming neutral atoms for the first time and causing the universe to become transparent. That ancient light, released at the moment when atoms first formed, still fills the universe today, stretched by cosmic expansion into faint microwave radiation that we detect as the cosmic microwave background. This radiation is not light from stars or galaxies, but a direct image of the universe when it first became visible, preserving a record of its earliest structure. By this time itself had acquired direction. Events followed one another in sequence, and cause led to effect. But time was not absolute, because its flow depended on motion, gravity, and energy. As the universe continued to expand, tiny differences in density imprinted during its earliest moments were stretched across space, forming the seeds from which all future structure would grow. Over immense spans of time, gravity amplified these irregularities, drawing matter together into vast regions that would eventually collapse to form the first stars and galaxies. The beginning of the universe was not a place in space, but a moment in time, and from that moment onward, the history of everything began. As this early universe continued to expand and cool, it carried with it the memory of its own beginning, encoded in the distribution of matter and energy across space, quietly determining where gravity would later gather material and where vast empty regions would remain. Nothing about this process was sudden or violent on human scales.
because the transformation unfolded slowly across immense spans of time, guided not by intention or design, but by simple physical laws acting on an incomprehensibly large stage. From these early conditions, the future paths of galaxies, stars, and planets were already being outlined, even though none of them yet existed, and the universe itself was still dark, silent, and waiting.
For a long time after the universe became transparent, there were still no stars and no galaxies, because matter was spread thinly across space, drifting slowly through darkness under the influence of gravity alone. The universe had entered what is often called the cosmic dark ages, a period when space was filled mostly with neutral hydrogen gas, faint background radiation, and vast regions of emptiness where nothing yet shone. Although the universe was expanding and cooling, gravity was quietly at work, amplifying tiny differences in density that had been imprinted during the earliest moments of cosmic history. In regions where matter was slightly denser than average, gravity pulled material inward, drawing hydrogen gas together over millions of years and slowly increasing pressure and temperature at their centers. These growing clouds of gas collapsed further and further until conditions became extreme enough to ignite nuclear fusion, marking the birth of the first stars in the universe. These earliest stars were unlike the stars we see today because they formed from almost pure hydrogen and helium and grew to enormous sizes, burning their fuel rapidly and shining with extraordinary intensity. For the first time since the universe became transparent, light was being produced locally, not as leftover radiation from the beginning, but as energy generated inside stars themselves. As these massive stars lived and died, they transformed the surrounding universe, flooding space with ultraviolet radiation that began to alter the state of intergalactic matter. This process, known as cosmic reionization, gradually changed the neutral hydrogen filling space into a plasma once again, allowing light to travel freely across vast cosmic distances. At the same time, the deaths of these first stars enriched the surrounding gas with heavier elements, forged in their cores and scattered into space through powerful stellar explosions. These newly created elements made it possible for later generations of stars to form with greater complexity, eventually allowing planets, chemistry, and life to emerge billions of years later. As gravity continued to pull matter together, stars gathered into larger structures, forming the first galaxies, bound collections of hundreds of millions or even billions of stars. These early galaxies were small, irregular, and chaotic, but over time they merged and grew, assembling into the vast cosmic structures that now fill the observable universe. Across immense distances, filaments of matter formed a cosmic web, with galaxies tracing long strands separated by enormous voids where little matter exists at all. By this stage, the universe had begun to resemble its modern form, with light filling space, structure emerging on every scale, and complexity increasing with time. The long darkness following the birth of the universe had ended, replaced by an era of light, motion, and transformation that would shape everything that followed. Over time, the light from these first stars did more than illuminate space, because it fundamentally changed the physical conditions of the universe, heating surrounding gas and reshaping the environments in which future stars and galaxies would form. Regions that had once been cold and uniform became dynamic and structured as radiation, gravity, and motion interacted across enormous distances, slowly transforming a simple universe into one capable of complexity. From this moment onward, the cosmos was no longer defined only by expansion and cooling, but by cycles of creation and destruction.
in which stars formed, lived, and died, leaving lasting imprints on everything that followed. As this era of the first stars unfolded, the universe began to change its character because light was no longer a rare remnant of the beginning, but a continuous presence shaping space, matter, and time itself across vast cosmic distances. What had once been a nearly uniform expanse was now marked by contrast, by regions of brightness and shadow, growth and collapse, signaling that the universe had entered a new and irreversible phase of its evolution.
As the first generations of stars transformed the early universe from darkness into light, gravity continued its slow and persistent work, shaping matter on scales far larger than individual stars, and gradually organizing the cosmos into vast, interconnected structures. Regions that contained slightly more matter than average began to grow over time, pulling in gas, stars, and dark matter, increasing their mass and complexity as the universe expanded around them. These regions became the first galaxies, enormous systems bound by gravity, where billions of stars formed, evolved, and interacted within extended halos dominated by invisible dark matter. Galaxies did not emerge alone or in isolation because gravity linked them across immense distances, drawing them into groups and clusters that moved together through the expanding fabric of space. Between these clusters, matter arranged itself into long filaments and broad sheets, forming a vast cosmic web that stretches across the observable universe and defines its large-scale structure. Along these filaments, galaxies formed more efficiently as gas flowed steadily toward regions of greater mass, while enormous voids opened between them, regions so empty that only a few galaxies drift through volumes of space millions of light-years across. On these immense scales, motion is almost imperceptible because galaxies travel slowly along gravitational pathways, their journeys unfolding over hundreds of millions and even billions of years. From this perspective, the universe appears less like a collection of isolated objects and more like a single evolving system in which every galaxy is shaped not only by its own gravity, but by its position within the cosmic web itself. From this scale, the distances between galaxies are so vast that light itself requires millions of years to cross them, reminding us that what appears static to human eyes is in fact part of a slow and continuous cosmic motion. Every galaxy we observe carries the imprint of its journey through this structure, shaped by where it formed, how it moved, and how often it encountered other galaxies along the way. Some paths through the cosmic web lead to crowded regions filled with clusters and constant interaction, while others pass through quieter environments where galaxies evolve in relative isolation over immense periods of time. Together, these varied histories create the diversity of galactic forms we see today, revealing a universe whose structure is not only vast, but deeply interconnected across space and time. Some galaxies grow quietly by drawing in gas from their surroundings, forming stars over long, steady intervals, while others are transformed through encounters and mergers that rearrange stars, reshape galactic forms, and alter their future evolution. This pattern did not arise by chance because it reflects tiny variations in density imprinted during the earliest moments of the universe and amplified patiently by gravity over cosmic time. Within galaxies, stars continued to be born and destroyed, recycling matter through successive generations and gradually enriching the universe with heavier elements essential for complexity. As the universe aged, galaxies settled into recognizable forms, including spirals,
ellipticals, and irregular systems, each shaped by environment, history, and interaction with neighboring galaxies. Even the deepest voids play a role in defining cosmic structure because the contrast between dense filaments and vast empty regions gives the universe its large-scale geometry and visual scale. When we observe the cosmos today, we are seeing the outcome of this long process, a universe woven together by gravity into an intricate network of matter and light. The cosmic web is not merely the backdrop for galaxies, but the framework that guides their motion, growth, and evolution across billions of years. By this stage in its history, the universe had become richly structured, luminous, and dynamic, setting the conditions necessary for planets, environments, and eventually life to emerge.
As galaxies continued their slow evolution across billions of years, the activity unfolding within them became increasingly complex, because stars were no longer isolated sources of light, but participants in vast, interconnected cycles of birth, transformation, and renewal that shaped their environments over immense spans of time. Inside the cores of stars, nuclear fusion operated continuously, converting lighter elements into heavier ones and gradually building carbon, oxygen, silicon, and iron, materials that would later become fundamental to planets, chemistry, and the possibility of life itself. When the most massive stars reached the limits of their stability, they ended their lives in powerful supernova explosions, releasing tremendous energy and scattering these newly forged elements far beyond their original locations, enriching entire regions of their host galaxies. Over long periods of time, this enriched material mixed slowly with surrounding interstellar gas, ensuring that each new generation of stars formed from matter that carried within it the accumulated history of many previous stellar lifetimes. Around a large fraction of these stars, rotating disks of gas and dust emerged gradually, shaped by gravity, motion, and angular momentum, creating the environments in which planetary systems could begin to form over millions of years. Within these disks, countless collisions took place as microscopic particles interacted, adhered, and grew, progressing step by step from fine dust to larger aggregates and eventually into planets following stable orbits around their parent stars. Some of these planets formed close to their stars and became hot, dense worlds, while others formed farther out, where temperatures allowed volatile compounds such as water to remain stable for extended periods of time. In a small fraction of planetary systems, conditions proved unusually balanced, allowing rocky planets to exist within regions where liquid water could persist on their surfaces across geological timescales. These environments did not guarantee the emergence of life, but they provided the chemical richness, energy sources, and long-term stability required for complex processes to unfold gradually rather than catastrophically. As planets continued to cool and differentiate, their interiors, surfaces, and atmospheres evolved under the influence of impacts, volcanism, radiation, and interactions with their parent stars, producing a wide range of planetary environments. On at least one such planet, chemistry crossed a critical threshold, giving rise to systems capable of storing information, replicating imperfectly, and responding to their surroundings in ways that allowed evolution to begin. Life did not appear suddenly or fully formed, but emerged through countless intermediate stages, shaped by energy flows, chemical gradients, and the persistent influence of its environment over immense spans of time. As life evolved,
it began to modify its planet, altering atmospheres, oceans, and surfaces, leaving detectable signatures that would persist long after individual organisms disappeared. From this perspective, life is not separate from the universe that produced it, but a continuation of cosmic evolution, arising wherever conditions allow complexity to persist long enough to take hold. The atoms within living organisms were forged in ancient stars, assembled on planetary surfaces, and organized by the same physical laws that govern galaxies, clusters, and the cosmic web itself. In this way, planets and life are not anomalies in the universe, but expressions of a process that began with the first stars and continues to unfold across the cosmos.
As the universe continues to expand, its future is shaped not by sudden catastrophes or dramatic endings, but by slow and relentless processes that unfold across timescales so vast that they exceed not only human history, but the full lifetimes of stars, galaxies, and even entire cosmic structures. Galaxies will continue to drift farther apart over time, not because they are moving through space like objects in an explosion, but because the space between them keeps stretching, carrying light, matter, and information steadily beyond the limits of mutual reach. Over billions of years, the rate at which new stars are formed will gradually decline as galaxies consume or lose the cold gas required to ignite stellar birth, leaving behind populations increasingly dominated by long-lived, faint, and slowly fading remnants. The bright, energetic universe we observe today therefore represents only a brief and temporary phase within a much longer cosmic story, one in which energy becomes more evenly distributed and large organized structures grow progressively rarer. As existing stars age and exhaust their fuel, many will end their lives quietly, cooling into white dwarfs, neutron stars, or black holes, objects that can persist for immense spans of time, long after visible starlight has largely disappeared. Planetary systems will often remain gravitationally bound to their stars for trillions of years, but without the formation of new stars, the universe will gradually transition into a darker, quieter state, defined more by absence than by activity. On even longer timescales, internal gravitational interactions will continue to reshape galaxies from within, while their separation from one another increases relentlessly, isolating each system inside its own shrinking observable region. If cosmic expansion continues indefinitely, distant galaxies will eventually cross beyond the cosmic horizon, their light stretched, weakened, and redshifted until it can no longer reach any observer, no matter how powerful their instruments become. From within any remaining galaxy, the wider universe will appear increasingly empty, with fewer visible structures and diminishing evidence that a vast and dynamic cosmic history ever existed beyond its boundaries. Matter itself may not remain stable forever, and over unimaginably long periods, even the particles that compose stars, planets, and living beings could decay, transform, or dissolve into more fundamental forms. Black holes, among the longest-lived and most extreme objects in the universe, will slowly lose mass through subtle quantum processes, evaporating so gradually that their lifetimes dwarf the current age of the cosmos by many orders of magnitude. In this distant future, energy will be spread thinly across space, approaching a state of maximum entropy, where large-scale structure, motion, and complexity become increasingly difficult to sustain. Yet even this outcome is not truly an ending, but the natural consequence of the same physical laws that governed the formation of stars, galaxies, planets, and life from the very beginning. The future of the universe is therefore not defined by collapse or destruction, but by continuous transformation, guided by expansion, gravity, and the irreversible flow of time itself. From the first moments after the beginning to the farthest reaches of the future, the universe follows a single, unbroken trajectory, connecting all epochs through cause, effect, and physical law. Within this immense timeline, conscious observers exist only briefly, capable of looking outward, reconstructing the past, and imagining futures that extend far beyond their own finite lifespans. In seeking to understand the future of the universe, we are also reflecting on our place within it, recognizing that we are part of a process far larger, older, and more enduring than ourselves. The universe will continue long after stars fade and galaxies drift apart, carrying forward the consequences of its beginning into a future that is quiet, expansive, and almost beyond comprehension. And although that future may be dark and silent, the fact that it can be understood at all remains one of the most remarkable outcomes of cosmic evolution.